So suppose we have a function whose domain is Rm and codomain is Rn. We can define that by matrix multiplication. M times V, where V is in Rm, equals W. So V is in the domain, vector W is in the codomain. M has got, the matrix M has M columns. So the number of columns is the size of the domain, and N rows. So the number of rows is the size of the codomain. And then the RREF either has a leading one or not. And the columns with the leading one serve as the basis for the range of this function. And we want to find an interpretation for the columns without leading ones. So we're going to mention a quick thing about linearity for matrices. So suppose we have W zeros in the range of the function, and V1 and V2 both get mapped to that point, right? So we have a function, it takes our vector space, we'll put 3 vectors in there to another vector space, right? And we have some W0 in the domain, and we have 2 vectors, V1 and V2, over here in the domain, and they both get mapped to the same place. Then what happens about the difference of these two? I think this is V2 minus V1. Well, where does that get mapped? So if 2 things get mapped to the same thing, where does the difference between them get sent to? Well, the difference between them, we know we have linearity, so we can subtract, right? We can distribute the M, and then we get this, and then W0 minus W0 equals 0. And these are all vectors here, so they should have little arrows on them, right? So this difference, that gets mapped to the origin. That's surprisingly powerful because the difference between any 2 solutions to MV equals WZ has to be a vector that solves MV equals 0. And we give those a name that's called the null space. So all vectors that get mapped to 0 are the null space. So particular and homogeneous solutions, we saw this when we were doing differential equations. Suppose W is in the range of W0, and we have is in the range of the function. So here's our domain. It's some vector space. Here's our codomain, which is also some vector space. And we have some W0. And we know that some V0 gets mapped to it because it's in V0 gets mapped to it because it's in the range. So if we have another vector, V tilde, that also gets mapped at W0, then we know that M V0 minus V tilde gets mapped to 0. The difference between these two is mapped to the origin. But that means that V0 minus V tilde has to be equal to some vector n right? So this has to be a vector in the null space, right? So we'll call it n. So what is V tilde equal to? Oh, I should have done this backwards. Sorry. Call this V tilde minus V0. V tilde minus V0, just to get my signs figured out. Right? So V tilde has to be a vector in the null space plus a particular vector that goes to W0. So all the vectors that get mapped to here, right? If I know what the null space is, suppose the null space is some kind of plane, then all the vectors that get mapped to W0 are V0 plus vectors that are in the null space. So generally, when we're doing differential equations, we call this the particular solution. No, yes, we call that the particular solution. We call this the homogeneous solution. So that kind of breaking down into particular and homogeneous, that works for matrices as well as for differential equations. So here's a matrix. We want to know its null space. So what is the null space? With MV equals 0. But this is a 3 by 2. So if we set V equal to, say, x1, x2, x3, what is m times v equal to 0? That's this equation. So m times v equals 0 is 1, 5, 1, 2, 11, 5 times x1, x2, x3 equals 0, 0. And if we set this up as a augmented matrix, it's 1, 5, 1, 2, 11, 5, 0, 0. So that's the augmented matrix that we get for this matrix equation. And we grind into reduced row echelon form, and we get that. And you can find that easily by looking at a computer. So equation solution then is x1 minus 14x3 equals 0, x2 plus 3x3 equals 0. What does that give me? X1 equals 14x3, x2 equals minus 3x3, and we'll do our usual thing of setting x3 to be equal to t, a parameter. So what is our solution to this matrix equation? Well, x1 is 14t, x2 is minus 3t, and x3 is t. And then we can factor out the t. We get this. The null space is the span of that vector, right? Because it's everything that's a multiple of 14 minus 3, 1. So we set this equal to 0, we find the row reduced echelon form, and then you get a parameter. So here's our matrix. We want to think of this function now, mv equals w, as a function from 3-dimensional space into 2-dimensional space. Right? Because we take as inputs 3-dimensional vectors, we get as output 2-dimensional vectors. So here's a picture. This is the domain. This is the codomain. Red, green, and blue are our 3 unit vectors, I, J, K. Where do they go to in the codomain? Well, red is m times I, blue is m times k, and green is m times j. And we know these are linearly dependent because there's 3 of them in 2 dimensions. And we also see that from here, the third vector is dependent on the first 2. The purple vector here is the null space. Everything along this line gets mapped to 0. So one way to think about this function is if I got rid of z, I, j, and n equal to, what is it, 14 minus 3, 1. As a basis for R3. So every vector, if I plotted a vector out here somewhere, instead of using z, we'll say, well, this is some vector that is, oh, gotta do something like this. We go certain direction in the x direction, certain direction in the y direction. That takes me way out here. And then we go a certain amount parallel. The purple. Right? So we can take our vector and we can say it's something times a times I plus b times j plus c times n. And then what's m times v? Well, that'll be a times mi plus b times mj plus c times mn. But that's just a mi plus b mj plus 0, because that equals 0. It's a null space. So if this is a steps in the x direction and b steps in the y direction and c steps in the n direction, what happens is that I go a steps in this direction plus b steps of this vector, and that's where this vector here, that gets mapped to that, because what does the function do? It just erases this part and keeps this part, but transfers it over into the plane. So the null space, if we're going from 3 dimensions to 2 dimensions, right, we must have lost a dimension somewhere. And the null space is the dimension that we lost. We can keep the I and j, but if we replace z by n, then we just lose the purple direction. And I think that's all that I really wanted to say about that. So still working on with the same function, mv equals w0. So w0 is 1, 1. And both of these functions are in the codomain. They're kind of, both these pictures are in the codomain. No, this one's in the domain. This is 3 dimensions. This is the codomain. So what's going on here? We still have red, green, red and blue. That's mi. Blue is still mk, and green is still mj. So we have a vector in the, we're given a vector in the codomain, and that's this one. And we want to know what gets mapped onto that. And what our theorem said, it should be some functions, some vectors plus the null space. So mv equals w0 means that the solutions to this must be a particular solution plus vectors in null space. So the reduced row echelon form, that's this, tells me that the last column is equal to 6 times first column minus 1 times the second column. Right? So 6 times this column plus minus 1 times that column. And that will give us the solution to this equation. So 6 minus 1, a particular solution, is 6i minus j. Okay. And so that's this orange vector in here. And that's a particular solution that gets mapped onto W0. But this is our null space. This is the purple thing. So if I take another solution, so what's the other possible solutions? Well, other possible solutions are anything that lies along this line, which is 6i minus j as its offset vector plus the null space. right? So here's our offset vector, and this is a line parallel to the null space. So any vector along that line, in particular, say this vector, right, that lies on this line, this would also be a solution. And any vector that I draw that actually is on that line, that's actually also a solution. So what we know about the null space is this we got from the RREF. The particular solution came out of the RREF. And then the null space is way up here. Did I write down where the null space was? Up here, T14 minus 3, 1. So any vector that can be written like that, that is a solution to the equation mv equals w. So what's m times 6 minus 1, 0 plus t 14 minus 3, 1. Well, that's the same thing as the matrix m times 6 minus 1, 0 plus m times this, but the t is a scalar, so that can factor out. And you get w0 because this is our particular solution. And then this is just m times something in the null space. So that's 0. So the structure of solutions then is generally particular solution plus the null space. So here's a matrix, the REF. What we want is mv equals w. So this is the matrix M. This is the vector w0, and we want to know what's the solution to this equation. And that gives us a particular solution is here. So V, we'll call it V sub particular, is 2I plus 3J. Because this vector is 2 times this plus this vector, so this vector should be 2 times this plus that vector. So what's the null space? Well, we get the null space by solving mv equals 0, and that becomes the same reduced row echelon form on the right, but with zeros down right column. So same reduced row echelon form, but zeros down the right side. And we think of this as being the coefficients of x1, x2, x3, x4. So what are the equations we get here is x1 plus 5x2 equals 0. Oh, forgot about this one. X1 plus 5x2 plus x4 equals 0. And the second row becomes x3 plus x4 equals 0. So x2 becomes a parameter because it doesn't have a leading one in it, and x4 becomes a parameter. So set x2 equal to r, x4 equal to s, and then what do we have? Our null space is actually a plane. Let's see, x1 is equal to 5x2 plus x4. Well, x2 is r and x4 is s. So x1 is minus 5r here, minus s, and x3 is just minus s. And we'll break this into two vectors, one with all the r's in it, and then one with all the s's in it. And then we can factor out the s and the r. So the null space is the span of that. So what's the mechanics of this function? This is a matrix. It takes us from 4 dimensions, which is the number of columns, to 4 dimensions. And we lose 2 dimensions along the way because our null space is 2-dimensional. So a function goes from R4, which is a 4-dimensional space, to R4. We could take, looking at this, we could take E1 and E3 as a basis. So we can take as a basis here E1, which is 1, 0, 0, 0. Once we get up to 4 dimensions, we're not using ij and k anymore. And E3, which is 0, 0, 1, 0. And then we can also take as a basis N1 minus 5, 1, 0, 0, and N2. These are the vectors that span the null space. Minus 1, 0, minus 1, 1. And so every vector in the domain can be rewritten as K1 E1 plus K3 E3 plus J1 N1 plus J2 N2. J1, J2, K1, K3 are just scalars. And in the codomain, we apply the matrix to this vector, that's going to be K1 M E1 plus K3 M E3 plus J1 M N1 plus J2 M N2. But this is 0 and that is 0 because that's in the null space. And so MV equals K1 M E1 plus K3 M E3. And E1 is this vector. This is ME1 is the first column, and ME3 is the second column. So what are the mechanics of the function? We start with 4 dimensions. We have 2 dimensions that are spanned by the, that is the null space. And then we have 2 other dimensions. And then what the function does, it takes everything in the null space and squishes it down to 0 and just leaves you with the other 2 dimensions. And the other 2 dimensions are scrambled a little bit depending on what the numbers are. That's kind of what matrices do. So same thing here. This is going from R3 is the domain, equals number of columns. R3 equals codomain, equals number of rows. Looking at this, there are no parameters. So null space is just the 0 vector. right? M times 0 equals 0 for any matrix. So what's going on here? This is our matrix M. This is our W0. And so what is W0 equal to? There's only one solution because the null space is 0. So if you can find out a particular solution to this, then you've got a solution. And the solution is, oh, this is W0, my bad. This vector here, this column, is the solution vector V. So V equal to 11 halves minus 8, 57 over 2 is the only solution to the equation MV equals W0, where W0 is 2, 3, 4. Okay. So the columns with the leading ones in the REF are basis for the range of the function. The columns with no leading ones are related to the null space of the function. And here we get a really useful thing. Dimension of range, dimension of domain is the number of columns in the matrix. What does that equal? Number of columns with leading ones plus, of course, number of columns without leading ones. But the number of columns with leading ones is the dimension of the range, and the number of columns without leading ones is the dimension of the null space. So every dimension of the domain either is preserved, right? It goes over into the range and becomes part of the dimension of the range, or it gets sent to 0, and then it goes into the null space. So here's a matrix and it's RREF. What's going on here? So dimension of domain, 1, 2, 3, 4, 5, 6, 7. Codomain, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we're going from 7 dimensions to 10 dimensions. And what we see here is the dimension of the range equals 7. So what does it tell us about the dimension of the null space? Well, that has to be 0, right? Because there's no parameters there. So what's going on with the mechanics of this function? Well, we're taking 7 dimensions, put it into 10 dimensions. The range does not equal the codomain because the codomain has got 3 extra dimensions in it. But the range is actually 7-dimensional. So we don't actually lose any vectors, any dimensions. We just take our 7 dimensions and we just push it into 10 dimensions. And our 7 dimensions, none of them collapse into a null space. And so we just have 7 dimensions covered out of the 10 that we have available. And that's about all that happens there. Okay, so for finite dimensional vector space, what we've seen is that there's a number of dimensions for REF. REF can be a solution to a system of equations. REF reveals relationships among the vectors in a collection, and the REF, you can think about it as data required for thinking about matrices as functions. So here's a set of equations. Find the REF, and then you can use the RREF to solve the equations. Well, so if we have a set of equations, we want to turn it into an augmented matrix. The first column is the coefficients of x1. The second column is the coefficients of x2, then the coefficients of x3, and the coefficients of x4 and the coefficients of x5. We put a bar, and then we put the vector that we're interested in the image. Okay, so if the RREF is this, what does that tell me? It tells me that so it tells me that if I take x1 equal to 1, so we turn these into solutions. So this is equations become x1 plus x3 equals 1, x2 plus x3 plus x5 equals to 1, and then x4 minus x5 equals minus 1. Right? And we can rewrite that as x1 equals 1 minus x3, x2 equals 1 minus x3 minus x5, and x4 equals minus 1 minus x5. So x3 is one parameter, x5 is another parameter. And it tells us that solutions are x1, x2, x3, x4, x5. 1 minus s, x2 is 1 minus s minus t, x3 is s, x4 is minus 1 minus t, and x5 is just t. And we can do our usual thing. We'll break out a vector, and then we'll have s, a minus 1 here, and a minus 1 here, and a 0 there, as those are the three terms that have s's in it, and plus a t, 0, minus 1, 0, minus 1, 1. So what does that tell us? Well, this is a solution, 1, 1, 0, minus 1, 0, and then plus any number times this vector plus any number times that vector. So if we write this as a solution, then if we want to think about this set of equations, we get this RREF, and the RREF can be turned back into equations, and that gives us all the solutions. So a set of vectors, what are the linear relationships between the vectors? Well, this is the same batch that we get here, actually. But we want to know what's the relationship between these 6, right? What we do is we take these and we turn them into a matrix. So if we want to find out what the linear dependencies are, get that. And then what does this tell us? If we call this V1, V2, V3, V4, V5, this tells us that V1 this is V3. V3 equals V1 plus V2. So this column is this plus this. And this column, which is V4, is V2 minus V3. And then V5, V6, sorry, which is this column, is V1 plus V2 minus V3. Or we have linear dependencies between our vectors. 3 of them are independent, and the other 3 are not. So we have V1 plus V2 minus V3 equals 0. We have V2 minus V3 minus V4 equals 0. And we have V1 plus V2 minus V3 minus V6 equals 0. And these are all vectors. So what do we have? We have, this is V1, 2, 3, 4. This is actually V5, V6. This should be V5 here. 5 there. And so literally independent vectors, that's 3 of them, and I can write the other 3 in terms of those. So those are linearly dependencies. It's the same reduced row echelon form as above. Matrix M, use the reduced row echelon form of this matrix, the domain and codomain. Use the RF to find a basis for the null space in its range. So here's our matrix M. Domain, number of columns, 5. Codomain equals number of rows equals 3. So let's see, basis for the null space. You take our RREF and make it a augmented matrix with zeros on the other side. What does that become? X1, X2, X3, X4, X5. So X1 plus X3 equals 0. X2 plus X3 plus X5 equals 0. And X4 minus X5 equals 0. And we already know those equations because that's exactly what we had up here, except here we had the 1 minus 1, 1, 1, and minus 1 floating around. So these two vectors, right, this is actually our null space. Minus 1, 1, 1. I think that was correct for S. Go back up, minus 1, and then minus 1, minus 1, 1. I think that was T. 0, minus 1, 0, minus 1, 1. 0. 0, minus 1, 0, minus 1, 1. Scribble that out. So that's our null space. What's a particular solution to this? W0 equals 3, 0, minus 6. Right, so this column is 1 times that column, plus 1 times that column, plus minus 1 times that column. So that's a particular solution. We can ignore these two columns. And that gives us that the solutions to MV equals W0, where this here is W0, are going to be of the form 1, 1, 0, minus 1, 0, plus, that's our particular solution, S minus 1, minus 1, 1, 0, 0, plus T 0, minus 1, 0, minus 1, 1. And so that gives us our particulars, but that gives us all our solutions. And so we can sort of see what's going on here, right? Is that we always sort of come back in solving equations, we come back to something like this. This is the particular solution that we actually picked up way up here in solving these equations. And then this part is the null space. That's a particular part. This is the null space that we picked out from dealing with this. And then this part here is saying, well, we've got these 6 vectors, and now we're not thinking of V6 as being a solution. It's just one more vector. We want to know, is it in the span of these 5? And the answer is that it is. And in fact, that we have these relationships between the vectors. And you can solve for V6 in terms of the others by using these equations. So reduced for echelon form gives us a lot of different things. So that's explaining the connections there. So matrix multiplication is an example of a wider phenomena, that of linear transformations. So linear transformations is anything that satisfies this, that t times a constant times a vector plus another constant times another vector. You can factor out the constants and then split apart the addition. Anything involving all the stuff that we've done with matrix multiplication, null space and range in particular, that carries over to linear transformations. In finite dimensions, linear transformations, all linear transformations are matrix multiplication with REF, but in infinite dimensions, we don't have an REF to work with. So we want to think about that a little bit. Many linear transformations that you'll see, Laplace transforms, we'll see later in the course, Fourier transforms if we take partial differential equations, but the most important for us is differentiation. So differentiation, if A and B are constants, we know that this is that, right? So we can differentiate each function, multiply by its constants, and then add them together. So if we use d instead of d by dt, right, it's exactly a linear transformation. So, right, when we say d of e to the 2t, that's 2e to the 2t. The derivative of cosine of t is minus sine of t. So d just stands for differentiation. What's the null space of that? Well, the null space is derivative, and we want to know what are all the functions so that the derivative of a function equals 0, and we know what that is. That's the constant functions. Uh, so what does that have to do with the plus c in calculus? Well, if we want to solve the derivative of a function equals to a function, what does that mean? The solution is f of t equals a particular solution plus null space. Right? A particular solution plus the null space of the derivative. And so the plus c is just the null space of the derivative. And so if we have solve, say, d of f equals to t squared, we know that f of t is 1/3 t cubed. That's a particular solution plus a constant, and that's the null space. And so the null space of differentiation is the homogeneous solution, right? And then that's a particular solution. So solve this then. We write it like this. And this is what the notation is. And we know how to solve this because we did this before. Um, right? There's a homogeneous solution. You'd guess y equals e to the alpha times e to the 7t, which we've done down here somewhere. And the particular solution is 1/9. So particular solution is y sub p equals 1/9 e to the 7t. So what is the solution to our equation? We think of these things as vectors. What we have is a line. Usually instead of k, we use t before as one of our parameters, or r and s. But here, traditionally, we use k. So this is a parameter, and it varies. And then this is, we could think of this as being an offset vector. So out here in function space, what we have is a particular solution. And then we have our direction vector is this. And so here's the line of solutions in function space. And that allows us to think about solutions to this sort of equations like that. So product rule. The interesting thing about the product rule in this notation is actually what we're interested in is the product rule for t times a function. The derivative of t is just 1. Right? And then t times the derivative function. So that's what the product rule is. So null space of second differentiation means solving this equation. Oops, equals 0. Derivative, the derivative of the derivative of y equals 0. And we'll often just write that as d squared y equals 0. So second derivative of y equals 0. What does that have to be? Well, we know y equals a constant. The second derivative of a constant is a derivative times is the derivative of the derivative of constant. Derivative of constant is 0, so it's just the derivative of 0, which is just 0. But suppose we have a solution, dy of t. Let's do a general thing here. Suppose something is in the null space. So what's the derivative, the second derivative of t times y if y is in the null space? Well, that's the derivative of t times y, which is this. But this is 0 because we assume that y was in the null space. So it's d of y, but that's 0 because y is in the null space. So the nice thing about multiplying by t the product rule, is here's where the multiplication by t came from, right? If y is in the null space of the derivative operator, then ty is in the null space of d squared. So in particular, the null space of the differential second derivative operator is our lines, because C2 is constants are the derivative, are in the null space of the derivative function, and then constant times t times constants are the other solutions. So the null space of d plus 2, how do we find that? You solve d plus 2y equals 0. We already know that that's y equals k e to the minus 2t. What about the null space of d plus 3, d plus 2? Well, this means that we take a function y and we differentiate it and multiply it by 2. So in more familiar terms, this is dy dt plus 2y. And then we take d plus 3, d plus 2, y. And that means that we want to take the derivative plus 3 of this function. And so we get d squared y dt squared plus, you get a 2 dy dt, right? We're just basically foiling everything out. Dy dt applied to this gives me a 2 dy dt plus another 3 dy dt, which gives me a 5 dy dt, and then plus 6y. We want all this to be equal to 0. So if we're thinking about function space, here's my function space. Here's 0. And we're going to start off in function space. And we have a function d plus 2, which differentiates things. And then we have another function d plus 3, which differentiates things again. And we want to start over here with y. We want to end up here on 0. So what's the null space of d plus 2? Well, if I take the line k e to the minus 2t, right? So there's a vector in the null space and then the span. We know that all gets mapped to 0 here. So this is in the null space. And then if we take d plus 3 mapping to 0, so this whole null space gets mapped to 0. But there's another null space going through there, which is k e to the minus 3t is the null space for d plus 3, and that gets mapped to 0. So what functions get mapped onto this? Well, we know that those are just going to be other functions in the form e to the minus 3t. So this space actually gets mapped to itself by d plus 2. So we end up with two dimensions in this, two lines in this function space, and they span a plane, a two-dimensional space, and that's because we did differentiation twice. So And that's why we only needed two functions to span our general solution. We had left that question hanging for a while. And then finally, what's the null space of d plus 2 squared? Right? What's everything that satisfies this? Well, we know that that is true. And then we want to know what's another function right? So we want to start with sets of functions, sets of functions, sets of functions. We know k e to the minus 2t, that this whole line here gets mapped to 0. And we know back here in our function space, so this is d plus 2. Back here in our function space, we know that the same line, k e to the minus 2t, that gets mapped to 0 by d plus 2. But what's another function that gets mapped to e to the minus 2t? Well, how can we solve that? Well, we know, let's just rely on the product rule again. We know this is in the null space of that, of d plus 2. So if we multiply by t, same thing as we did above, we get that equal to 0. So we have another vector out here, k2 equals to t e to the minus 2t. And so that gives us our two-dimensional space that solves that. And that explains where the t comes from. And so if we solve this, note that this is d plus 2 squared, y equals t. And so solution will be a particular solution, which is going to be of form mt plus b, plus the null space, which is e to the minus 2t plus k2 t e to the minus 2t. And that ends up linear algebra for the moment.